let's spend some time talking about ideal solutions. So we have a solvent and a solute, and your solute can either be volatile or non-volatile. And I think the diagram that we've looked at together already considered a solvent with a volatile solute, and so we talked about an ideal solution being comprised of two liquids. But let's consider a non-volatile solute for the moment. I always want to have my composition for a binary system phase diagram on the x-axis, and that is my written as mole fraction. It's convenient, it's unitless, and I know that my limits are from 0 to 1. So the choice I have here at the moment is whether or not to put a mole fraction of the solvent or a mole fraction of the solute. But now let's think for a moment before we decide that, and think about what's on the x-axis. So I'll tell you that the x-axis for us at the moment is in terms of pressure. This is actually going to be the vapor pressure. And so if I can illustrate here, think that you have a vessel with your solvent and your solute, so it's a solution, ideal. No heat exchanged with the surroundings when it's formed. Ideal solution, no net strong forces to contribute to any enthalpy of mixing. So single phase solution, so the solvent and the solute are there, but I want to close it, so I'm going to put a lid on, like so, not too straight, and that way I have a vapor above the solution. And I'm not going to describe it more than that for the moment. So that vapor, of course, has a vapor pressure that can be measured and plotted, and that's what my y-axis is. So I have my solution, and the solution is going to be a certain composition. Now, the vapor pressure will be 0. Let's back up a moment. Let's consider first, that I'm talking about a non-volatile solute. So alone, it doesn't have a vapor pressure. It's like a powder. So I had a solvent, I added some powdered solute to it, I mixed it up. It's clear solution again, and I still have some vapor pressure above the solution. Clearly, the molecules in that vapor are not from the non-volatile solute, but rather the volatile component, which is the solvent. And so my pressure, which is the vapor pressure above the solution, is going to be 0 when I have no solvent present, and the vapor pressure above a mole fraction 1 for the solvent means that I have pure solvent, is actually going to be the vapor pressure of that pure component. So I'm going to label this as the vapor pressure, and let me call my solvent equals A. So in my binary system I have A and B, and my non-volatile solute is represented by B. So when the mole fraction of A is 1, I have my highest pressure, and that is P star, and the star, this guy here, I'll change my color, that indicates a pure liquid. Okay, that star indicates pure, and so this is pure of A. All right, and I know that it should be 0 down here. Now, because it is ideal solution, okay, because it's an ideal solution, I'm looking for a straight edge. Here's a good straight edge. We'll use Vancouver. I know, I should have a ruler handy. Okay, we'll use a ruler next time if I find one. Yeah, because it's ideal, I'm going to just wander down here to explain that that line is straight. Now, that line you can think of as having an equation, and it's a straight line. Y is pressure, X is mole fraction. Whoops. Sorry about that. Okay, we're back in view. And it's basically an illustration of Rayleigh's law. So this is the vapor pressure. This line is made up of points that represent the vapor pressure at any composition. So let me just take a point to illustrate, and I would move over to the Y and drop down to the X as well to give me coordinates. And here, this is my composition in terms of the mole fraction of solvent. And this would be the value of the vapor pressure above the solution of composition mole fraction of A, of this one in particular. And we know, how about I move that up? We know that that vapor pressure, just hold on one second. Fix my microphone. We know that that vapor pressure is a fraction of what it would be of the pure, which is still in view up here. So if I don't have any solute, then the vapor pressure is that of the pure liquid at that temperature. And you can see that the more solute I add, the more concentrated the solution, the less number of molecules there are available at the surface of that liquid to escape to the vapor phase. So this line makes sense. And it makes sense that it's a straight line and has no curvature to it because it's ideal, and so I don't have any extra effects of those A-B molecules exerting forces on each other that would either push more molecules into the vapor phase or restrict some because of their high affinity for each other. And so it is a straight line. And so these are all vapor pressures above the solution, and I can say that that vapor pressure above the solution is equal to a fraction, mole fraction, of what it would be as a pure liquid. Got it? Okay. And okay, when would the vapor pressure, I haven't finished this because as you can tell I need a subscript here to define this. Is it A? Is it B? Is it liquid? Is it vapor? It's liquid here obviously, but is it A or B? Well, when would this equal this? The vapor pressure above the solution would actually equal the pure vapor pressure of that liquid if all I had in there was A. In other words, if this were equal to 1. And so this is the mole fraction of A. So I can see that as this fraction increases to a maximum of 1, that's my limit where these are equal. Okay. Oops. Okay. So that is the effect of the non-volatile solute. Now what's really neat, I'm flipping pages here, there's a diagram. There's a diagram in your book. Yeah. I want to maybe keep these videos not married to a particular edition. So instead of giving the exact page number and so on, I'm just going to reconstruct that diagram that I'm referring to. So it looks a little bit, looks like this. And it ties in really nicely with what we've just done. So this is the chemical potential, and this is temperature. And I know that, and of course the context here is that it's a constant pressure. So, say out on the bench. I know what d mu by dt at constant pressure is. We know that this, you spent a lot of time on this in class, is equal to, you want to take a stab at that? Do you remember? So du is also the same for a pure component as the dg. Yeah, so that was the case where we started with a fundamental equation g, wrote dg, divided through by dt, constant pressure. We ended up with the molar entropy. Okay, so can't get all of that in view, but that's the negative molar entropy, which means that the slope of this is equal to the molar entropy. And so the slope should be steepest, therefore, for my vapor phase, least steep for my solid phase, but all sloping in a negative direction. So this is, you'll recall us doing this in class, hopefully. I'll just switch pens. We did a steep line, and then a not so steep, and then another even still sloping, negative slope, but not as steep. And we drop these perpendiculars as labels, nice and straight. And basically what I've done, because that's temperature, and this is for a pure component, okay, consider this pure component A, so it relates to the above. So it would be like A without any solute in it. And I'm not too concerned about the solid phase. I'm quite concerned with the liquid phase at the moment. And this is vapor. All right, so this clearly would be the melting, and this is the boiling. Now, what happens, here's the question, and this is a big question. What happens to the chemical potential of pure liquid A when I add my non-volatile solute to it? What happens to it? Or to any solute, whether it's volatile or not volatile, it doesn't matter. What happens to the chemical potential? Does it stay unchanged? Would it increase or would it decrease? What happens to the chemical potential of the liquid when I make a solution from unmixed to mixed? Well, we know the formula for chemical potential. So let's move down here. We know that the chemical potential. I'm just going to make sure I'm doing the same nomenclature. So the chemical potential of that liquid, pure, is equal to, do you remember? It's equal to the chemical potential for the pure liquid at a standard pressure plus RT ln. So this little bit here is kind of tweaking this because, say, that's not at the standard pressure. It's at this temperature. It's the ln of pressure, and because this is pure, this is PA pure. So that makes sense. The chemical potential of the pure liquid is equal to the standard plus RT ln the vapor pressure of A pure. Now I would look that up in a table. That's a table value. Right? You just locate the temperature, find this in a table. You locate the temperature and you look up A, and it'll tell you what the vapor pressure of A should be at that temperature. Okay, so this is pure. Let's make the notes complete here. So this is for the pure liquid A. Now, quite literally, we are going to add solute and make a solution. So now A is part of an ideal solution. A is the solvent, the major component. Now I will write, and you've got this in your notes, that the chemical potential of A, I'm not going to use the star now because it's part of, it's not pure, it's part of the binary system. But it's still always related to that same reference point, the standard, plus RT ln of, now it's not the vapor pressure of the pure component, but it is the partial pressure. Okay? Right. So, what's the moral of this story? Well, we would say that the chemical potential of A is less than the chemical potential of A pure. It is less. It lowers the chemical potential. So how does that translate into this graph? Let's think about that. How would I illustrate that? I'll let you think. I'm going to find out who's been emailing me. Right. Here's a hint. You're just going to focus your attention on the middle of that graph because we're talking about A as a liquid. And when I add solute to A as a liquid, I lower the chemical potential. So think about that straight line sloping, and maintaining that slope, but the chemical potential is lower. So in fact, let's lower it and see what happens. I'm drawing it parallel to the existing one. So this now is for the solution, whereas the one above, of course, was for the pure component. Got it? So what happens now with the solution? See, you already know what happens, but maybe you haven't seen it depicted quite like this before. What happens, you look at your diagram now, what happens to the boiling point now for the solution? What is the boiling point for the solution relative to the boiling point of the pure liquid? Yeah, it's now boiling at a higher temperature. See these lines? So I get what's called a boiling point elevation. That's one of the so-called colligative properties. Yeah, and what's neat is that, I think it's neat anyway, if it forms an ideal solution, it doesn't depend on what your components are. It actually depends on just how much solute you have. Colligative literally translates as relating to number. Yeah, so it's a real effect on the entropy. Okay, so when I have a solution, the boiling point is higher. Interesting, because if I go back to my little sketch of this solution, see, when I have now some A solutes in it, which I'll do that, now I have less numbers of molecules of A at the surface that are going into the vapor. Yeah, so I'm not explaining it in terms of intermolecular forces, like they're not holding on to it, and therefore I need more energy for it to vaporize, because then it wouldn't be ideal. Like we already established that, yeah, that this was an ideal solution, and so that's why it's a pure colligative property. It's just dependent on number. Okay, so what's the effect on the freezing point? The freezing point now, see where it was for the pure liquid? Now it's lower. Couple of things to notice here. Oh, I've put freezing versus melting. You know those are the same thing. Yeah, just depends on the direction. Freezing, I'm going to put this right away, or melting. It's up to you. Doesn't look like an error. Or TM. So see what happens? So you get a boiling point elevation and you get a freezing point depression. Yeah, you've heard that before, right? Freezing point depression. So I'm going to write that in here. This is now getting to be a busy diagram. But I think it's okay if you actually started at the beginning. If you jump into the deep end, so to speak, in this video, you may get a little lost. And that's a second colligative property of solution. The third and final is osmotic pressure, sorry. Gosh. So, and I'll just let you read about that one. It'll make sense after these, because it's just an effective number related to diffusion. So, a couple of things to notice. One really important one is that the margin of elevation does not equal the margin of depression. There's I don't remember if it was last year or the year before, but there was a first-year chemistry book we were using, and yeah, which reminds me, if you want to look at a basic view of this, look it up in a first-year book. It's done really well. Well, except in this particular edition, a couple of years ago, I think. They somehow drew this so that this margin and this margin were equal. It was a poor sketch. Yeah, but the freezing point depression is greater than the boiling point elevation, and the reason for that goes back to these slopes being different. So again, it goes back to how you're disrupting the relative disorder in the different phases, and goes back to number. So this pink line here, I've just lowered the chemical potential for the liquid in solution, so this is going from pure to solution. I didn't bother doing it for the vapor because that doesn't make sense, and nor does it make sense for the solid. So that's why that diagram only has, for the solution, one line, because the solution only affects the liquid phase of what becomes your solvent, as opposed to being the pure liquid. So it's really kind of neat that you can depict that whole creation of a solution, making a solution, on this diagram, and we know that this diagram is so very important. So why would the freezing point be lower? So think about your cooling curves. You were starting at a high temperature, and you were lowering the cooling it. You're lowering the temperature at constant composition. Let's say you did it for the pure first, so you'd record the freezing temperature for the pure liquid, and then you do it for the solution. You have to cool it down a lot more, right? So that's what's happening here. So this is really the freezing point of the liquid freezing out of solution as a pure solid. And as you know, when it boils, it only boils A out of solution. It doesn't take the B solute with it. That's a kind of a principle. We wouldn't be able to separate things through distillation if that were the case. Yeah, so how come this margin is so much bigger than this effect? Well, again, it comes down to number. And so if you're cooling, you've already made your liquid a little more disordered by adding B solute, non-volatile solute. And so in order for A to freeze out and pack nicely into a crystal, you actually have to extract out more thermal energy for that to happen. Yeah, because you've disrupted A by adding solute B. Okay, so lots to look at there. I'll just maybe give you the last view to make sure that you've got it all in your notes. And that was a good discussion of a couple of graphs for a non-volatile solute making an ideal solution with a solvent. So the next one, we'll do the volatile.